Hi, so today we're going to be going over the recently released LLAMA 3. So LLAMA 3 is a new model that just came out, one of the best open source models of all time. This is the third one in the series. It came out just today, and today we're just going to be going over the architecture and basically how it works. So LLAMA 3 is a transformer model, and they say that they released a 8B and 70 billion parameter version that can be used for just about anything: code generation, summarization, writing emails. So their models, LLAMA 3, 8B, and 70B, are the best available models at the 8B and 70 billion scale. And these are some of the performance. So note, LLAMA 3 outperforms everybody, including Gemma, Mistral. There's only a couple things in which Llama, Gemini 1.5, and Cloud outperform it, but Mistral, Meta outperforms Gemma, Mistral, Gemini, and Cloud all at the same time. And they tested it with these evaluations. I don't really like evaluations. I don't think they're really useful. But LLAMA 3 does reach a new state-of-the-art at these scales, at these benchmarks, which is very interesting. Like I said, I don't know too much about evaluations. I think they're mostly a scam, or like they're not really grounded in reality. But here's the model architecture, which is why we're here. The model architecture behind Llama is it's very simply put, a series of transformer blocks that don't use regular attention. This is regular attention. Okay, so they use the new Llama 3 uses grouped query attention. So in the regular old multi-head attention, every query, every key, and every value map together. In grouped query, well, you could define it, of course. You can set the parameters. But here we have two queries for every one key and value. And multi-query is just multiple queries into multiple values. Now, theoretically, the grouped query approach is kind of the best, because let's say you have a search. You want to search up Llama 3, right? There's going to be many different types of queries that you can search for this value of information. So it's like a query is like a Google search, a value is like a web page, and a key is like the title. That's how I want you to think of this. So they're using the grouped query attention, which is very new. It's only released in like the last 6 months or something. So compared to Llama 2, it made several key improvements. Llama 3 uses a tokenizer with a vocabulary of 128,000 tokens that encodes language much more efficiently. Now, what they're talking about is the OpenAI tokenizer. So the Llama 3 tokenizer is essentially tick token, which is the same tokenizer as GPT-4. And so previously, the Llama tokenizer was Sentence Piece, which is another tokenizer by Google. And I heavily recommend that you go and watch Andrew Karpathy's video on tokenization. It's the undisputed best video right now for tokenization. And I personally need to watch it, because I'm going to be honest with you. Tokenization is like kind of underestimated area of machine learning. Basically, what a tokenizer does is transforms a bunch of language and text and characters, it could be text, it could be emojis, into a bunch of integers, so that those integers can then be converted into tensors. So it's a three-step process, really. You have some text, say like Llama 3 is state-of-the-art. Basically, what this needs to happen is this needs to be converted into a bunch of numbers that represent those tokens. And that's essentially what That's essentially what a tokenizer does. And then this gets converted into tensors, which are the inputs into the model. So without these tensors, there would be no, without these tokens, there'd be no efficient way of converting text into actual, tensors that are easy to input into a model. So if we go back to the blog, so they have 120,000 tokens. That's one of the big improvements they said. We've adopted grouped query attention, what we talked about, at both AB and 70B. We train the models on sequences of 8,192 tokens using a mask to ensure self-attention does not cross document boundaries. Now, a couple things in here. A lot of people have been getting confused with self-attention and grouped query attention. Self-attention is basically the same. Self-attention is basically just regular old attention. Doesn't mean anything new. A mask, though, what a mask does is mask. Basically, a mask is like a mask essentially turns. You have a tensor, which is like an array, and that basically a mask just transforms some of those values into zeros. So like this is a tensor, these would just be 0. And so that way the model doesn't need to compute attention on those and saves energy. And that's also how it predicts. So you have to mask out some tokens. We're going to get into the model architecture, but I quickly want to go over this. So the training data. To train the best language model, the creation of large, high-quality data set is paramount. They invested heavily in pre-training data. 15 trillion tokens were collected from publicly available sources. The training data set is 7 times larger than the data set that is used for LLAMA 2, which is quite big. To prepare for upcoming multilingual use cases, 5% of the LLAMA 3 pre-training data sets consists of non-English data that covers over 30 languages. No, to ensure LLAMA 3 is trained on the data of the highest quality, we developed a series of data filtering pipelines. These pipelines include heuristic filters, whatever that word is, filters, semantic duplication, text classifiers to predict data quality. So they use LLAMA 2 to generate the training data for the text quality classifiers that are powering LLAMA 3. Essentially, they use LLAMA 2 to find the pre-training data sources that LLAMA 3 are using. And so scaling up pre-training, they develop a whole bunch of custom stuff that they use to train LLAMA 3. They made some new observations on scaling behavior. While the chinchilla optimal amount of training computes for an 8 billion model corresponds to 200 billion tokens, we found that model performance continues to improve even if the model is trained on 2 orders of magnitude of more data. Both our AB and 70B parameter models continue to improve log linearly after we train them up to 15 trillion tokens. LLAMA 3 was trained on more than 15 trillion tokens. Wow. Larger models can match the performance of these smaller models with less training compute, but smaller models are generally preferred because they are much more efficient during inference. Now, this is another thing. They combine 3 types of parallelization: data parallelization, model parallelization, pipeline parallelization. So let's see if we could quickly find a diagram of this. There was one before. I gotta find it. So essentially, they made it very easy to split up the data sets over many different GPUs. So they split up the data sets, they split up the model, and they split up they're essentially finding the best way to train a model given very large data sets on very large numbers of GPUs all at the same time. And so I recommend going into this. This is pretty crucial in understanding how LLMs like this are trained. I'm not gonna. Maybe we'll make a video about that in the future. So, wow, they utilize over 400 teraflops per GPU. They perform training runs on 2 custom-built 24,000 GPU clusters. I wonder if they're A100s. To maximize GPU time, they created a whole new training stack. So they have hardware reliability detection mechanisms for silent data corruption. And we developed new scalable storage systems that reduce overheads of checkpointing and rollback. Now, very interestingly, they use a couple of RL techniques here. Our post-to-post training is a combination of SVT, supervised fine-tuning, rejection sampling, proximal policy optimization, PPO, and the widely popular now DPO, which is direct policy optimization. The quality of these prompts that are used in SFT and the performance rankings that are used in PPO and DPO has an outsized influence on the performance of aligned models. Some of our biggest improvements in model quality came from carefully curating this data and performing multiple rounds of quality assurance on annotations provided by human annotators. Basically, they just had humans, like essentially go over the data and rank it and just give it some metric. Learning from preference rankings via PPO and DPO has greatly improved the performance of LLAMA 3 on reasoning and coding tests. We found that if you ask a model for a reasoning question that it struggles to answer, the model will sometimes produce the right reasoning traits. The model knows how to produce the right answer, but it does not know how to select it. Training up preference rankings enables the model to learn how to select it. That's some secret sauce right there. And that's pretty much it. This is the propaganda section, how they brainwashed it. And that's pretty much it. Let's go into the code. So this is a code base. They released it. And let's see. So this is how you can use it. Kind of simple, but we want to get into the actual architecture here so we can understand how this bad boy works. So let's jump into it. Now first, I don't know why we import some stuff. They're using Torch and Fairscale to Torch is amazing. I absolutely love Torch. I do not like Fairscale. There's not a lot of documentation for that, unfortunately. And I don't know why people do this. This is such a bad programming practice, and especially for PyTorch people. I don't know why they're doing this. PyTorch is supposed to be a very Pythonic language. This isn't Python. It's not pure Python. So they're creating a class of the arguments instead of just giving the class that has the arguments those arguments, but instead they're giving it to all of them. Very bad practice. The dimension's 4096. They have 32 layers, 32 heads. This is the grouped query attention, so you specify how many keys and values, vocab size, multiple of. This is for Swiglu. This is the feedforward dimension, the normalization epsilon, and the rope theta. Max batch size is 32. Max sequence length is 2048. Now they had a sequence length of 8,196. So the first class here is the RMS normalization, root mean squared normalization. This is very popular now. A lot of models are using this. And essentially what they do is they have some parameters here. They create a weight of a bunch of ones of the dimension size. Then they return x times the root squared of the x, what's power? The power of each element input with exponent returns it. Okay. So they take a power of each element and input with exponents. And then they get the mean, and then they add the epsilon. So then they norm it, then they output, they multiply this with the weight. Now, the paper for Rubin square normalization is really, really good. Check it out. A lot of models use this. Basically, what RMS norm and layer norm does, if nobody will tell you this, basically what the normalization does is it helps essentially cut down the training instability of a model. Let's see if we can find a visualization of this. Basically, if you wanted to visualize this, it takes a bunch of random information and just like, there you go. So read this paper. Essentially organizes a bunch of what would seemingly be a bunch of random data in a way that is somewhat symmetrical in this shape. And RMS norm does that same thing, but with less running time, basically. Yeah, so RMS norm is very popular. I suggest you check out the paper. Essentially what it does, again, is reduces training stability and essentially symmetricalizes, if that's a word, the data. This is pre-compute frequency. This is for the embeddings, rotary embeddings. We're taking the frequencies 1 divided by the theta divided by the torque terrain float. Then we're arranging again. We're getting the outer and polar. What's polar again? Constructs a complex tensor whose elements are Cartesian coordinates corresponding to the polar coordinates with absolute value yeah. So reshape for broadcast. I like what they do here. They add the types. I think, well, adding types, especially for mathematical things. I'm a dynamical types person, but adding the types here is really good. Because this is mathematical and like things can be ints, things can be floats. Just put your types. They make this function pre-compute frequencies. Reshape for broadcast, which is they're taking in a tensor and another tensor, checking to see the shape. Then they're applying the rotary embeddings. They're viewing as complex, reshaping for broadcast, viewing as a real. Then they have another utility function called repeat interleave, where they're essentially like they're taking the shape of the tensor. So anytime you can get the shape of the tensor, if you know the shape, you can get it. You can get the batch, sequence length, number of heads, and the dimension. By just doing this, you have to know it. If there's 3 text for text things, it's going to be 3. So Lucid Reigns pioneer that. And then so finally we get to the attention, where they're going to add up rotary embeddings and everything else into the attention. Taking in the parameters, they're setting some things up. Then here we have a bunch of linears. So they're taking in a linear, the first WQ, most likely the query, is they're going to take a dimension size and then they're going to multiply the heads with the head dimension. That's going to be the output. So the second is going to be like here, the input, this is the input dimension, and here's going to be the output. So we have the number of heads, head dimension, column parallel linear dimension. We're doing the same thing here. Then we're reversing that. The cache, the KEV cache, you probably heard of it, is mostly just torch zeros of the size of batch size, sequence length, local KV heads, batch size, sequence length, KV heads, head dimension. So after that, we got the forward function, which is taking in an X, start positions for each seeks, mask. Again, they're getting the shape. They're applying the linears. They're applying the linears. They're viewing the tensors. They're reshaping them. They're applying the rotary embeddings, applying the cache. Then they're querying the cache for the keys and values. They're repeating the KVs, transposing now, getting ready for the attention. Then they're matrix multiplying the queries and the keys, and they're essentially going to compute the softmax of the values. Then they're going to multiply it again and transpose them, and basically just attention. Then here we have a feed forward dimension. The input is dimension, hidden dimension, multiple of, and the FFN dim multiplier. So there again, they're playing. They're putting 3 linears. So they're using SciALU, which is interesting. Sigmoid linear unit, or otherwise commonly known as the swish. I don't know why, but I like this name. So the first thing we do is they did this really bad. I don't know why they did. This is very hard to understand. They're just applying these linears with these activations. That could have been made better. And then finally we get to the transformer block. And before we go any further, let me just break down what a transformer is. So a transformer is simply attention with an FFN. That's it. Now, there will be n number of these, so there will be like, I don't know, it depends on how many you want really, but that depends on the layers. I think here was something like 32, but you could define the number of layers. So basically what the architecture here is, basically you have attention. This then goes to the FFN in a loop. So this will happen once, twice, and then it'll just keep going until you stop it. So you could also add norms here. A lot of people do norms plus residuals. You can customize this quite a bit, but mostly a transformer block is very simple. It's just attention and a feed forward. And that's exactly what they're doing here in this code base. So here they have a transformer block. They're specifying the attention, the feed forward, and some RMS norms. And we get to the forward, which is the special sauce. They're saying the H equals X plus, which is the inputs, plus self-attention of the attention norm X. And so essentially they're applying attention on the normalized value of X, and then they're essentially then they're adding this with the feed forward and then normalizing it. And so to visualize this, we can do this. Let's say this is the input tensor. So they're applying norm, they're applying a norm. Oops. Applying a norm. Then that's going to the attention. But this is a residual. A residual is just basically like, they're just adding up the output of this with the value from before. And then so this is then going to be they're then going to apply, they're going to get another residual, and here basically. And then they're going to, let's see, so yeah, they're going to add the residual with the feedforward applied to the FFN norm. So let's visualize that. So attention. So this is going to be the second residual. Then this is directly going to go into the FFN. And then the FFN is going to be like kind of like the final output. And then this will get sent into what is known as the output head, which is a norm, a linear, and then softmax. Linear to vocab size. And that's pretty much it. That's the whole model right there. You have an input, you normalize it. You're going to add this input with the output of this pretty soon. Normalize it, do attention, you have another residual. And then you essentially just add that, and that's pretty much it. That's a transformer model. Probably could have designed this a little better, but basically, let's see if we could find. Yeah, so this is a pretty good way of, there you go, basically. Input, attention, layer norm, residual. You're going to add the output of layer norm with this, or FFN, layer norm. So we do that there. Then here we're specifying the tokens. Vocab, we're going to get the embeddings of the vocab size. So this would be 125,000, and the dimension, which is 4,096. We're then going to create a list of transformer blocks, individual blocks, using this. We're going to specify as layers equals to torch10 module list for layer ID and range. We're going to append the transformer block. We're going to also initialize the norm and more linears. Then we're getting the shape of the tokens, which is going to be mostly two-dimensional as random integers. So these are going to be integers. Then we're going to transform those integers into tensors with this. Then we're going to apply the cell frequencies, and we're going to apply mass. If mass is none, then if sequence length is greater than 1, then mass equals torch.full sequence length, floats negative.inf, mass.reorg. What is that again? Returns the upper triangular part of a matrix. So there you go. Mass equals the torch stack, torch 0 sequence length. And then they're going to apply the list of transformer and NM blocks n number of times for the number of layers, each start position, frequency, mask. Then they're also going to normalize the output, which is a good practice, and then they're going to perform the output, which is going to be a linear from the dimension into the vocab size. And that's it. That's the model. Basically, this is a good diagram. There are some hidden things in this that they won't talk to you about, like that nobody really told you. Nobody really told me that the output head was these three things. It was kind of hidden deep within the original attention as all you need paper. And so the output head is a normalization, linear to vocab size, and then a softmax. And that'll be essentially what the tokenizer will decode. So this will give you the logits, and then this will be the actual tokens. So if we say like tokenizer decoder. So tokenizer can encode information into integers, and it could also decode those integers back in actual text. So we're going to essentially map that into a bunch of integers. This is going to be the tokens. And then we're going to convert those tokens into tensors, which is going to be the X. And then, whoa. And those tensors will be the inputs into the tensor. And that's pretty much it. Again, the flow is text, tokenizer encode, tensors. Tensors are the X, norm, tension, add from the beginning, residual, FFN, layer norm, output head, norm, linear, softmax, tokenizer decode. And that's the full model. That's how Llama 3 works. Now, if you're confused about any of this, you should watch the tokenization part, very important. How does a model know how to convert text into tokens? You should watch Kaprati's video on this. He's done an amazing job. And then the transformer, there's many things here. Normalization's big component, tension. And again, a transformer block equals tension plus FFN, feed forward, n number of times. You can use norms and residuals or skip connections as well. But mostly a transformer block is just tension plus feed forward. And that's essentially it. Grouped query tension is the best form of attention there is. There's not a better version of attention. So yeah, that's how model Llama 3 actually works. I'll give a pretty conclusive list of resources in the channel in the description. If you like this, please subscribe, please like and comment, and join our community. I don't know how much longer it'll be open, so you should probably want to join now. We have around 6,500 of the best AI researchers on the planet, including Jeremy Howard, who is amazing. And essentially, we've created more than 500 models in the past 10 months. Models like Gemini, multi-model Mamba, mixture of Mambas. We're the first people to make these types of models. So join up on our community and help. Let's create some fucking models. Let's go. Thanks for your time.